Hi guys, in this video I'll be taking you through a second example, slightly different from the first but essentially the same. Here we have got a case where A is negative, so let's see, and I've used a mapping notation instead of the function notation. So what you may want to do is to write this in terms of a function notation and say g of x is negative x squared over 2, right? Minus 1. Now, let's just quickly go through the range and the domain. As expected, domain is R, and the range, what is Q? Without even computing it first, we can see now. Let's consider first, A is negative, you are said. So if you are said, what did I say? Then your range, remember you are said, right? So your range, you are moving from Q downward. So your range, you'll say y less than or equal to, in this case, what is Q? Q is negative 1. Okay, then that's it, we are done. And you can see if you were to work on this, let's start. X squared will always be positive, yes. Now, if we're going to multiply by negative on both sides, then we know the inequality sign has to change, and that's why it changes there. And so we have a negative, and then we subtract 1 on both sides, and we get the fact that, oh, okay, this thing actually has, it bounces around negative 1, basically. And so we can see we can now start to have a clear picture. You know, when you draw your Cartesian plane, you don't really have to bother much. You can't have more space for the positive y-axis because you don't even going to get to any positive y value when you sketch this. You're actually going to end somewhere here at negative 1. So this, as I said, determining the domain and range first informs your scaling. So you could have actually a Cartesian plane that looks something like this. So that is your y, and this is your x. The y, the positive y, you don't have really much of a space because your graph is not going to even touch there. So you create more room for the negative space. Another interesting point why I selected this example is the fact that if you're going to find the intercept, you will actually realize that the solutions or the roots, I spoke about roots, are not real. In other words, the graph does not cut the x-axis. This is the implication here. And how do we see that roots are non-real? Notice that we have a square root of a negative number. And most of you say it does not exist. I understand that's okay, but it actually exists. You will learn that if you were to study maths further. So we refer to this case as, by saying rather, that here roots are non-real. Okay, so there are no x-intercepts. X-intercepts are there if roots are real. Okay, that's why I chose this example. And then finally, let's look for the y-intercept. It is there, of course. Q, you will notice by now that it seems like Q is usually the y-intercept. Okay, of course, when the graph is in this form, then sure, we can get to that. Okay, when you get to grade 11, you'll see things start to be a little bit interesting, and we can't always get the y-intercept when things are like this. You get, just to stimulate your interest, you will get something like g of x is equal to x minus 2 all squared plus 3 maybe there. And you can see here, you can't conclude that this is the y-intercept. Okay, so for now, because we're introducing you into this, you will always be lucky and find that Q is your y-intercept. Finally, determine the axis of symmetry. And in this case, usually, as we said, x equals to 0 does hold. This will not always be the case, especially in the grade 11 level. Okay, for now, as I said again, you'll be quite lucky. This will be the case in most cases, right? And now, because we established that this thing does not cut the x-axis, it might be a good idea to find 2 additional points that can help you to have a nice cup or cap. By the way, what are we having in this case? A negative. We are having a cap, okay? Or we are sad. So in this case, we may want 2 points that will lie somewhere there since the graph does not cut the x-axis, okay? So we're gonna have roughly a graph like that, okay? So you may use either x equals to plus 2 and minus 2 or x equals to plus 3 and minus 3. I have used both. And so let's look at the fourth condition. The fourth condition is that you must find the turning point. Let's see what the turning point is. Here, as you can see, the turning point is, we always take it from the range. I'm sure you would have noticed that is the routine. And so we had this effect that we have our range as y less than rather -1. So our turning point will be 0 and a -1. In fact, the axis of symmetry kind of also give us that clue. So this is the point where the graph will turn. And so let us have a look at the sketch. And here's the sketch, guys. I hope if you did pause the video at some point to try this on your own, I hope this is something that you got. And as you can see, it does not cut the x-axis anywhere, but plotting either this point when x is 2 and -2 would have helped us to get a nice shape, or that point 3 and -3, x equals to 3 and x equals to -3 would have also helped. You don't really have to put a whole lot of points, just few points to give you the leverage to join the dots, okay? So that's about it from me, guys. I want you, as usual, to give this a try. So go ahead, guys. Before we move on to the next topic, go ahead and give this a try. I want you to spend the next few days this week working on this. Work on it, try it. You don't understand? You know our WhatsApp line by now. Click that link in the website that says WhatsApp and ask Mr. G, how can I do this? Or Mr. G, am I correct to do this? And so forth. And we will help you when we are available. Otherwise, that's about it from me. I'll see you later when we look at problems that involve the quadratic function. Cheers.